Okay, so we're taking a look at number 5 here. I noticed, first of all, for sure that the rope makes an angle. So I just know I'm going to have to deal with that, right? So there's that. It says it's 400 newtons, but I know that there's going to be a piece that's Fx, and there's going to be a piece that's Fy. So I just need to keep that in mind. Again, what do I want to do? I want to do a free body diagram. I want to do equality and graphing annotations, and then I want to go to the math. Okay, so this says the rope connecting the truck and the crate makes an angle. There's the angle right there. The rope drags the crate along a horizontal surface with a 400 Newton force. The crate has a mass of 50 kilograms and the coefficient of friction. So there's a lot of information here. I think I might just come over here and say, say what it is. These things are given because it's kind of getting a little complicated. So 21.68 degrees. The force, I guess tension would be a good enough way to do it, is 400 newtons. Force, tension, and the X is going to be, let's take a look at it. I think I'll just go right here. Looks to me like they want us to say, okay, so so FG would be on the box by the earth. Yeah. All right. Now, if there's a force this way, which is the force tension, right? So this is force tension on the box by the rope, right? So I'm just going to come over here and do that so I can think about it as I draw. So this is F tension X, and maybe I will say this could be F tension Y, right? And I could say that the hypotenuse is 400 newtons, okay? And then the theta, right, is 27, whatever. Okay. So the F tension X is going to be cosine because it's adjacent to the angle, right? So F tension X is going to equal F cosine theta. Just a quick review. Cosine theta equals adjacent, which is that piece, the side, over hypotenuse. And in this case, the adjacent is F tension X. The hypotenuse is 400. So cosine theta equals F tension X over 400, or 400 cosine 27.68 degrees equals F tension X. Okay, so F tension X, 400 cosine 20, did I say 27? It's 21.68. Okay, so that's going to equal 371.7 newtons. And then force, let's go ahead and then force tension Y. So F tension Y is opposite, so it's going to be F sine theta, right? So it's going to be 400 sine newtons sine 21.68 degrees, and F tension Y. Notice how I'm not leaving any empty equalities. And then F tension Y is going to be 147.8 newtons. Okay, so I'm going to put that over here, 147.8 newtons. Okay, so this is the stuff I have. So first they want force weight. Okay, so they want for FG equals what? Okay, so I really haven't, I shouldn't be starting on this because I haven't finished. Okay, so let's finish the free body diagram, right? Okay, so the actual free body diagram, I feel like I have not put everything on here. So there's definitely a normal force. So if I look, G is down here. Is the normal having to carry all of G? No, because the normal's getting help here, right? So I'm going to say that the normal in my head, force normal, right, plus whatever's in the Y. I should probably, you know, let's see. Okay, so if FG on box, right, by Earth, and then the normal is going to be here. And let's say that's 3, and this is 1, and this will be 2, right? So I do know that the equality for the y is FG, right? And force normal, if it were just on the flat, normal would be carrying the whole basket. But now normal plus FTY are carrying the weight, right? Okay, so we say FG equals so what we want is we want to say that there is no F net, so the equality in the Y is that FG equals these two, right? So that's enough for right there. Okay. So let's look at the in the X. So the X equality statement in the X is, so what's happening in the X? Well, I don't think I have it all on here. Is there friction? There's a what coefficient of friction? So that tells me, yep, there's some kind of friction back this way, right? Okay, and I'm going to have fx. Now, I don't put that on the diagram, but I am going to have it, okay? So let's do equality in the x direction. I'm looking for whether or not, let's see, the rope drags, there's a force, the crate has a mass, blah, 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 blah. So, well, here's what I must say. There must be an unbalanced force, I think. The rope drags the crate. So it's dragging the crate with this force. The crate has a certain mass. There's a friction coefficient of friction. If the truck begins at rest, determine. So if it's being dragged, if it started at rest, x naught and v naught equals 0. Okay, if it started at rest and it's being dragged, we know that there's an acceleration, plus they ask us for it, okay? So that means it's not equal in the x. So what we know is it's going from, here's our picture, but it's going from, I'm just going to make that the origin, v naught equals 0 to v naught to v final equals something, right? So A is in this direction. So when the V and the A are in the same direction, then we know it's speeding up, right? So that means the unbalanced force, that means the Ftx minus F friction must equal the F net in the X direction, right? So whatever this is minus whatever this is must equal the F net. Okay? Great. So now that we've done equality statements, we haven't looked at the graph. It's going to go from, what does it do? It's being pulled, blah, blah, blah. We don't really have any. I'm looking for time. I don't see any time as a given. All right, I might have to wait. Sometimes you have to wait on the graph to have a little more information. Okay, so FG, easiest way to get FG if you can is just to say MG, right? So can I do that here? 50 kilograms times 10 newtons per kilogram? Sure, so that's pretty easy. 500 newtons. All right, there's one. Boom. All right, the normal force. Now here's the, don't swing at a pitch in the dirt, okay, guys? They're asking you this because they're trying to see if you'll write 500. But the normal and FG are not balanced here because remember, normal is getting help. So I can say that the normal, I can go right here and say FG is 500 newtons. Yeah. And F normal is what we're looking for, plus what we found FTY is 147.8 newtons, right? So this is the thing that has to be balanced, and the normal doesn't have to do it all by itself. So it's going to be 500 newtons minus whatever help it's getting from that Y component of the tension is going to equal force normal. And so in the end, that's 342.2 newtons. Okay, great. All right, then so we got that. The next one is force friction. So I think I might just do that right here. Friction equals mu force normal. I just found force normal, right? So force friction is, so coefficient of friction is 0.6. Force normal is 342.2. So force friction is 205.3 newtons. Great. Boom. Okay, so what's the acceleration? Well, I mean, there are lots of different ways to get acceleration. So, I mean, I could look at V equals AT plus V naught. I could look at anything that has an A in it. I could look at sum of F equals M A. To me, that looks like the easiest, right? Because, let's see, what's the, so the F net is X, F tension X minus F friction, and I have both of those, right? And I have M. So that seems like a pretty fast way to do it. So tension X is 371.7 minus friction, which is, what do we say, 205.3 newtons, yeah, over 50 kilograms equals A. So A equals, what do you think, 3.3 meters per second? Okay, so if I wanted to go back and see this graph, if it started from rest, I feel like if I make the slope 3.3, right? So, if I make the slope 3.3, so if I label this and everything and I draw it in such a way that it's 3.3, then I can find out how far it goes by finding the area, okay? I can also, of course, say X equals 1/2 A T squared plus V naught T plus X naught. It starts from not ahead or behind. It starts from rest. So I just end up with 1/2 of the acceleration. And just a second. So the last little bit is just, they want to know how far it goes in 10 seconds, right? Not the whole thing. So then I put in 10 seconds, and then we have 165 meters. So good deal.